So what I want to do next is talk a little bit about polyprotic acids. And polyprotic acids are simply acids that have more than one hydrogen. So a good example of polyprotic acid would be sulfuric acid, or later we'll talk about, for example, carbonic acid, H2CO3. But a couple of things to make note of. The first ionization of a strong acid, polyprotic acid, is always the strongest ionization. Now, it's not always strong. In the case of sulfuric acid's first ionization is a strong acid. Its second ionization is a weak acid, although it is still relatively high on the Ka list for weak acids. So, if we're thinking about what's going on then, right? In the first ionization, let's say I have a 0.2 molar solution of sulfuric acid, and I wrote it as H2A, so I didn't have to write sulfate over and over again. What's going to happen is that's going to completely ionize. So like a strong acid, mixture of HCl and a weak acid, that first ionization, that HCl, is going to produce both HA minus, and it's going to produce hydronium in the concentration of 0.2 as well. Now, unlike the mixtures of acids, though, HA minus is actually the starting point for the next reaction, and the hydronium is also in the reaction, but it's as a product. So what I did is I set up the ice table, and what we're going to do is assume that the first ionization is strong, and now we pick it up at the second ionization ice table. So we have H2SO4, sulfuric acid, 0.2 molar. So after that first ionization, I have 0.20 molar of hydrogen sulfate. Again, the water doesn't matter, and something happened to my equilibrium arrow, I don't know what. And then this is 0, okay? And the hydronium, I filled it in as 0.2, just like it was for mixtures of strong and weak acids. Now what you're going to do is you're going to say, well, it's going to go to the right because I have 0. I have 0 for my sulfate concentration, so it has to go in this direction. So it's going to be plus x here and plus x here and then minus x here. So I have 0.2 minus x, 0.2 plus x, and x. Now, I went ahead, and that's all plugged in here already, so we didn't have to do the work. You have to solve for the value of x. Now, it could be tempting at this point to say, oh, well, I'm just going to ignore x and assume it's small. But look at how big this constant is, right? This is 0.012. It's not 100 times smaller than the concentration. So, in fact, you can't do the x is small approximation. You still have to check these things instead of just doing them, right? So now I have to solve it for the value of x. When I do that, I get 0.010. Oh my gosh, thing's not writing. 10773. Only 2 sig figs. I carried maybe too many. Now to calculate the pH, what I have to do is combine those two values, because this is the hydronium now. So hydronium is going to be 0.2 plus, or 0 plus 0.010773, or 0.210, and then we'll just call that, we'll just round that to 1 at that point. My pH calculated from that is actually 0.676, or, sorry, I ran out of space, 0.68. Okay, so go back over what we did, right? It's very similar to mixtures of a strong and a weak, except for when you have a polyprotic acid. Not only do we populate the hydronium from the strong acid, but we also populate the acid from the strong acid. So this is an acid anion. The conjugate base of sulfuric acid goes here. So then we follow the normal course. We say minus x and plus x, and then we pop it into our equation, and then we evaluate whether or not we can assume x is small. But because this value is so big in comparison to the concentration, I don't make that approximation. I go ahead and solve the equation. And then again, as we had with mixtures of acids, the value you get for x does not determine the pH. The value you get for the 0.2 plus x in this case, or the hydronium from the first ionization or from the stronger acid, plus the hydronium from the weaker acid. That's what determines your final pH. I did actually wanted to mention one other thing as we move into the next problem. And I'll be honest with you, I didn't check these values with the current textbook. But where did I get those, right? And it's easy enough to say they're in the book. But what I did, if you go over to Canvas, and let me unzoom out of here. This is actually Appendix 2 from the 4th edition of Tro. And if you remember, I popped that into the resources section of the class Canvas page. So that's an easy way to find these. Now, I think these are the same in all the editions, but you would be surprised to see how many people list different values because they looked them up from different sources. They're probably all well referenced, but depending on the situation in which they were collected or measured, those values can change quite a bit. So what I did is I looked up carbonic acid, and I got 4.3 times 10 to the minus 7. And I looked it up in another source. Here, it's the second ionization. So when you have a polyprotic acid, it has more than one proton. It'll list the first ionization and then second ionization, and then for citric acid it has three, third ionization. And they'll list them as Ka1, Ka2, and Ka3. So that's where these things come from. You'll notice sulfuric acid is down here. This one's a strong acid for the first one, and you notice there's not many of those that are polyprotic where the first one's strong. But sulfuric acid, the first one is strong and the second one is weak, and so they list an ionization constant for it. Okay, so back on this problem, we have 0.1 molar carbonic acid, and it has two ionization constants. One of the things I did want to point out about the two ionization constants is they're usually really different. You couldn't see that in sulfuric acid because oh, and you notice I didn't use the value that was in your book too. I apologize. So if you do this problem, and I can't remember I signed it. If you do it, make sure you use the values in the book if you want to match what the book has. So you couldn't see it in sulfuric acid that these exponents are really different because when they list it as strong, they don't list the exponent in there. But typically these are about 4 to 6 orders of magnitude different, which means, right, this acid ionization constant represents an acid, Ha-, that's about anywhere from 10,000 to 1,000,000 times weaker than this ionization. So in a sense, when we're going to do these calculations, most of the hydronium actually just comes from this first ionization, and very little of it will come from the second. But it's important. There's some interesting things that happen when we go through the calculations, so we're going to go ahead and do that. So we're going to set up this ice table, and actually I'm not going to finish it all the way out, but I do want to show a couple of things on it. Of course we can draw our lines in. Initial, change, and then we'll have equilibrium like this. And we'll talk about how we're going to solve this problem. And if you'll notice down here, I actually show the quadratic solution for it, but we're going to talk about when and when not to do that again. So we're saying this is 0.1, right? And then initially these will both be 0. And then this will be minus x and x and x. And then I have 0.1 minus x. I'll have x here and I'll have x here. So think about what's going to happen in this problem. There's your hydronium ion concentration, but here's your conjugate base. And if you look at the next ice table, right, it's going to have the conjugate base as its starting material. and hydronium as a product. And this is very hard to grasp initially. But this reaction, this first ionization, is producing a product and a reactant of the second ionization. In a sense, it's easier to look at just both equations first, here, and recognize that when this is made, it goes in here. And when this is made, it goes in here. Okay? So, let's talk about how we're going to now solve this. Now, again, you can set it up as a quadratic and solve it, and that'll work just fine. But if you'll notice, this concentration is 0.1 from the previous slide, 1,0 actually. And this equilibrium constant is 10 to the minus 7. So that's 10 to the minus 1, 10 to the minus 7. It's way more than 100 times. And so it's easy to approximate this. So when you see that, you should just pretty much immediately go x is equal to the square root, right, of C times Ka. And that's going to be square root of 0.10 times the Ka value, 4.3 times 10 to the minus 7. This approximation is so good that when you go to get it, it comes out to be 2.07 times 10 to the minus 4. It's exactly the same as what you would have gotten if you'd set this up in a program and run it. Okay, so now this value feeds into the next reaction twice. So I have my ice table, right? And then I have 2.07 times 10 to the minus 4 here. And then I have 2.07 times 10 to the minus 4 here. So this is going to be minus x. Now there's no A2 yet, no conjugate base of the bicarbonate ion made yet. So we're going to have a 0 here, so it still goes to the right. And then at the bottom, I'm going to have 0.02 times 10 to the minus 4 minus x, and x, and then 2.07 times 10 to the minus 4 plus x like this. Now, you could probably still approximate this as x is small, because if you look at the concentration that you have here, right, this value is much, much smaller than the equilibrium constant. I mean, much, much larger than the equilibrium constant, more than 100 times. And you have the common ion, again, hydronium, suppressing the ionization, so x will be even smaller. So, you notice I wrote the equation down here, and this is what I wanted to talk about. If you solve it, you get 4.8 times 10 to the minus 11. Okay? So I said Ka is equal to, and I used y actually when I put it down here, and maybe I should have used y's up here. But when I wrote this in the text that I typed, I used x's and y's so people wouldn't get confused. So if y is small compared to this concentration, right, then it's small in both places. And as a result, you can scribble this out and ignore it. Now, what do you have then, right? You have 2.07 times 10 to the minus 4 times y divided by 2.07 times 10 to the minus 4, and you can cross this out like this. And y is equal to 4.8 times 10 to the minus 11. And why is this funny? Because it's equal to the equilibrium constant. Okay, and this always happens in these problems. The second ionization of a solution containing only one polyprotic acid, so there's no other things in there, the second ionization is always equal to the equilibrium constant for that reaction. Now, if I want to calculate pH, right, that's when I would use this. But what do you notice? You could add 4.8 times 10 to the minus 11 to that, but it's not going to make a difference. It's so small now. So all the hydronium, this all comes from the first reaction. And the concentration of this, right, is just Ka2. And by the way, knowing this little factoid here might seem kind of trivial at this point. It comes in important in the next couple of chapters. So it's important that you keep track of that idea. Now, pH then would be negative log. Essentially 2.07 times 10 to the minus 4. And that's 3.68. Actually, it comes out 3.683, and I should write that, and then I round it to this point. Okay, so that's how you deal with calculations for polyprotic acids. You treat the first ionization independently from the second, and then you treat it just like we did for mixtures, really, of strong acids and weak acids, or mixtures of weak acids. The only difference in these problems is that, unlike the mixtures of weak acids, right, this ionization is not affected by the concentration of product from the previous ionization. In weak acid mixtures, we just started from a fresh ice table. Here you have to take this, in a polyprotic acid, the product of the first reaction is the starting material for the second reaction. If you do a triprotic acid, you go through the same steps. You'll do the first one, you do the second one, and then in the third one, you would drop in the conjugate base as a reactant, and hydronium comes down into the product.